Right. So we understood, right? We understood that take this example for instance. Okay, take this example for instance. The image quality is a bit poor, but still you saw something like this, right? For the fxy, for the given fxy is equal to x square plus 2y square minus 2x minus 2xy, you got this form. Like maybe you take 10, 20, 30, then you are getting this fgh kind of things, right? And the idea is like you saw, since the function is increasing radially, so the gradient direction will be outwards. So gradient direction will be outwards, that we saw. Okay, so gradient will point to the direction of steepest increase of a function. Okay, so therefore you can see fgh, the function is increasing radially, so the gradient is pointing towards that direction. Okay, so fine. So these ideas, this simple idea, lead to a family of methods known as gradient descent methods. Okay, so these above ideas, okay, these above ideas lead to a large family of optimization methods known as gradient descent methods. Fine. Okay, so what is our idea here? Okay, so the idea is what is the gradient descent method is, what is gradient descent method we are performing here? We are using the gradient information, we are using the information about gradients, info about gradients to optimize the function. Do you agree? We are using the information of gradients to optimize the function. That is the idea here, right? Okay. So actually, to write it mathematically, our job is to find x star vector. Okay, is nothing but argmin. Okay, argmin, which take all vectors bar, take all vectors x bar, and take the argmin of f of x bar. Okay, starting from an initial guess, from some initial guess. Always you have to take an initial guess. So initial guess is say x0 vector, right? So that's the idea here. I think, yeah. Fine. Okay. So how we do this? I will remind you about the Newton's method. I will remind you about the Newton's method. What was in Newton's method? We will start from an initial guess, go to the next point. But how we will go to the next point? We will go to the next point depending on the initial. That is true. The next point depends on the previous point, but also on two other things. What are they? No, that is correct. But you are missing something basic. What they represent? First and double derivative, what they represent? They tell you how much to go, step size, and in which direction to go. Okay, that's how we started. No, then only you got that you have to go in the negative of the derivative. D is minus f prime, right? So therefore, xk plus 1 vector is equal to xk plus hk dk. hk dk means hk means is the step size, dk is the direction in which we will go, right? That is how optimization method works, right? Okay, so such dks are known as the descent or search direction. Search direction means it is searching in which direction should I go so that I can reach the optimization point, which direction I will go. Okay, you can appreciate the method more once I show an image of myself in the next figure. Okay, so hk is the step size. Hk is the step size. Hk is the step size. How much to go, okay, and in which direction to go, so that you can reach the optimum value of the function. Okay, that is how almost all important optimization methods work. So you should be careful in that case, right? But you think if we are trying to minimize the function, okay, so what should be our job? What should we need? What should be the condition? If you want to minimize the function, you started from xk, you went to xk plus 1, so, and you are trying to minimize the function. So what condition you need? Based on this information I said now, you are at xk, you are going to the next point xk plus 1, and you want to minimize the function. So what condition do you need? This is where you need to use. If you are trying to minimize the function, the next iteration when you go and when you evaluate the function at that point, it should be less than the value of the previous point. The same thing we'll write. Okay, so xk plus 1 is xk plus hk dk such that f at xk plus 1 vector is less than f at xk vector. Isn't it? This is the basic idea we will use here. Okay, so to do this, we need a proper descent direction. To do this, we need a proper descent direction, that is dk. How to find that dk? We will learn ahead. Okay, so can we write about xk plus 1? See, we have the value of xk plus 1, isn't it? We have xk plus 1. Do you agree? We also need f of xk plus 1. Can we compute that? What do you think? F of xk plus 1 vector is nothing but f of xk plus hk dk. Do you agree? Can we use Taylor series expansion? Can we use Taylor series expansion? Yes. So, but be very careful that this is not a one-dimensional Taylor series. In one-dimensional Taylor series, you were using f of x plus h. If f is a simple function of x variable only, then you are writing it as f of x plus h times f prime of x plus h square by 2 f double prime of x in order of third order terms. Fourth, we neglect those things, higher order terms. But here it is not that. Here you have a vector. That means you have to do a multi-dimensional Taylor series or multivariable Taylor series. You have multiple variables. When you have multiple variables, so what will happen? Not much changes will be there. In derivative, just replace the derivative with the gradient and double derivative with the Hessian. That's that. Okay. So how can we do? So it is nothing but same Taylor series. This is equal to f of xk bar plus hk. Okay. hk dk actually transpose. Okay. You will know why it is hk dk transpose. Then take the derivative. That should be the gradient. Gradient of f of xk. Okay. Plus the higher order term. So we are taking the second order, that is Hessian and all, as higher order term. Okay. So you will have an error of order 2. There will be an error of order 2. Okay, the method is not fully accurate. There will be order 2 error. Okay, fine. Now, okay. Now can you see that what is delta f? Delta f means how much f has changed from xk. When you went to xk plus 1, what is the difference between f of xk plus 1 and f of xk? So what you do? Just the minus. So this is nothing but f of xk plus 1 minus f of xk vector. This is nothing but HK DK transpose grad F of XK. Don't you agree? Do you agree? But we have to be careful. I missed one thing that grad F is actually a vector and direction is also a vector. Okay, we cannot multiply two vectors. I mean, vector times vector, no, we cannot do. So we have to do, yes. Why dot product? Because, why she told dot product? Because here there is a vector, here there is a vector, but you are adding with a scalar f of xk. So that means this part has to be a scalar. If you need it to be a scalar, vector and vector needs to be a scalar, the only operation that can do is a dot product. The only operator that can help you is a dot product. Do you agree? Is it clear? Okay, good. And actually, this is something very nice. This is something very nice. This part here, which you are seeing right now, is very nice. Okay, so this is known as directional derivative. This is known as the directional derivative. Okay, directional derivative in the direction of dk vector. I hope you have known the term directional derivative in your previous studies. Okay. Else, I would like to ask you, those who have undergone multivariable calculus in their bachelor's or high school, they would be knowing this directional derivative. Even in physics, if someone has studied electromagnetics or electromagnetism or energy principles, they might have gone through this multivariable calculus. And you know that this is directional derivative. Okay, now fine. Okay. So what we want actually? What do you want? We want f evaluated at xk plus 1 is less than f of xk. So that means delta f should be yes, negative, less than 0. So we want delta f less than 0 for minimization. We need delta f less than 0 for minimization. If delta f is less than 0, what we need? Can you tell me now? Yeah. Yes. So you need, okay, let me be back. So you need, okay, dk transpose, okay. You need dk transpose. Observe that hk is a step size and always positive. Hk is a step size and is always positive. We don't have a negative step size, always a positive step size. So the only possibility is dk transpose dot product of gradient of f at xk vector is less than 0. That is the only condition left. Now, can we use the dot product definition? If you use the dot product definition, can you tell me what is the definition of dot product? So this should be the norm of dk transpose or dk, same norm of grad f at xk vector cos theta. Theta is the angle between the direction vector and the gradient. Okay, that is less than 0. Fine. Now this is a norm, so it should be greater than 0. It is also a norm, so greater than 0. That implies only thing that can turn this table around is cos theta is less than 0. If cos theta is less than 0, can you tell me for what angles? I mean, it can be any other values also. But if we have the choice, why don't we go to minimum? What is the minimum or least value of cos? -1. Okay, when it happens -1, pi. Okay, so theta equals to pi. That's where cos theta is minimum. You can take that value. Okay, theta equals to pi. Now, what does theta equal to pi means? What does theta equal to pi means? It is telling you, this implies that the angle between, okay, the angle between dk vector, the descent direction in your algorithm or numerical method, and the gradient of the function at xk is 180 degrees or pi. Okay, what does it mean? It means that dk vector is nothing but minus of grad f at xk, opposite directions. Yes, so you understood whatever we told in just intuition, that we have shown that it is actually the scenario through proof. We have actually shown you, but you saw how we are optimizing the cases. If it is actually minimization, then the next step iteration value should be less than the current step. Okay, then we are putting a condition and we are finding where it can be the steepest. Okay, cos theta can be minus 0.5 also, but we did not take it. We took where it is extremely minimum, final value, -1. So when theta equal to pi. Okay, you want that, right? So therefore, it turns out dk is minus of grad of this, right? So this is the condition here. So we have shown this. Okay. So the rate of minimization, is highest. Okay, is highest, I think, yes, is highest at this direction. The rate of minimization is highest in this direction. So this is one of the most important concepts here. The rate of minimization is highest in this, at this direction. Okay. So you should ask me, what is the meaning of rate of minimization? Okay. So what is meant by rate of minimization? Okay. So rate of minimization. Refers to the reduction of the value of the function over a unit distance. Do you agree? So rate of minimization refers to the reduction of the value of the function over a unit distance. If you go a unit distance, how much your function has reduced? Why I am telling the function value should reduce? Because we are looking at a minimization problem. So we want to go in a direction where function value should be minimized. So therefore, how much it is minimized, if we go in that direction, that is known as the rate of minimization of the function. I hope it is intuitive. You can think about it, right? Okay. Now you might be wondering that we are only giving priority to the direction, but actually there is a step size also. There is hk and dk, but till now we found which dk we should choose. So we should choose dk equal to minus of gradient evaluated at that point, negative of the gradient. But no one is talking about the step size. Okay. So what should you choose the step size? Here it leads to several optimizations. This is the case where it leads to several optimizations. And this is the case where you will find out that gradient method is not all in all. Gradient descent method is just a method, but you will find out that Newton's method sometimes overpowers gradient descent method. Okay, so here you will see that the gradient descent method is not all like the superpower method. There can be a Newton method which can be more efficient than the gradient descent method. We will see that using Python. So what about HK? That's the question. What about HK? That's what it is. So there are three methods actually. One is you can keep the step size constant. I mean, just go through 0.5, 0.01, 0.01 every time, fix the step size, but that is inefficient because it will take a lot of iterations to reach there. Okay. Another is you can update the step size at every iteration. At every iteration, you have this direction. So based on that direction, you go 3 step size. Now this direction, so you go 0.01 step size. Next, another direction, go 0.1 step size, 0.5 step size. So every iteration, you change the step size. That is also computationally intensive. Now there exists a third condition, third method that is referred to as a Armijo method. That means it's not a method, it's like a Armijo condition applied to a gradient descent method. Okay, what is that Armijo condition? It tells you that you don't have to change the step size at every iteration, rather than change the step size partial whenever needed. So whenever the Armijo condition is satisfied, change the step size. Okay. No, if the Armijo condition is satisfied, I think go with the gradient descent method. If it is not satisfied, change or scale up the step size into low. Okay. So that is a bit of a backtracking method, partial method. I mean, it's an adaptive method. If something did not work, you adapt. Something worked, go as usual. If something did not work, you adapt. You can see. So usually they can come by bus. If they did not get it, they can come by walk. Right. So that is adaptive. Okay. So this is means if condition fails, do this. Condition works, do that. So that is Armijo condition. 3 conditions. So we will see that if you use Newton's method of n dimensions, you will surpass all of them. Okay. I mean gradient descent won't work in that case. Okay. We'll see that. We'll see that. Don't worry. So what about HK? So this HK step size, this is not a vector. HK step size can be obtained through line search techniques. Line search techniques means those things, those 3 methods I told you. Okay. I mean descent direction and step size direction. You search along a line where to go. So what we are worried here is this one. So something like f of xk plus 1, okay, and this is equal to f of xk plus hk dk, right? And this, let us call, this is a function. Okay, now that we have our xk and now that we have our direction, descent direction dk, so technically it is only a function of h. So we can write it as a function of hk. Don't you think? Technically we can write it as a function of hk only. Why? Because we already determined the dk. Because that dk is equal to minus of gradient. So we don't have to treat it as a function anymore. But hk we have not established. So therefore we want to know what the step size we can vary so that the function can reach the optimum value. Right? So therefore this f xk plus 1 is equal to f of xk plus hk dk. We can consider it as a other function phi which depends only on hk, the step size. Okay. Okay. And our job is like minimize phi h. Don't you think? Minimize phi h. Minimize phi h means minimize f of xk plus 1. Don't you think? Is any problem? It's the same. I'm just giving a new function name, but finally it is a function only. Okay. So minimizing this, so minimize phi h, but this becomes computationally expensive. This becomes actually computationally expensive. Okay. I mean, if you keep constant step size, you have to keep constant step size and you have to reach here. Suppose this is your destination and you are taking very tiny steps, then it will take forever to reach here. So it will take a lot of computational time to reach there. And but you can tell, so take big steps. We cannot take, because we don't know a priori, we don't know from the previously that how much we have to take the step size to reach there, because at that time we don't know where is the optimum. So how much step size to take, we don't know. You are getting, if you know the destination, then you can know that, oh, I can jump and go. But here you don't know a priori the optimum point. So how will you decide how much to go? Maybe if you go far, your optimum point is here, but you made a jump like this here. You don't know in a priori. Usually in situations, if like given these values, you know a priori like which are the minimization points. But if given like a other functions where you cannot compute optimum before, then you cannot choose this. You are in the middle of the method. You have not reached the optimum yet. You are in the middle of a method. Okay. So there are different methods, like I told you, like constant step size can be adopted, constant h at every step, at every iterative step, and such are known as such are found to be expensive because computationally expensive. So to modify that, partial minimization is achieved. Partial minimization, like this is a bit adaptive technique, and this is what I told you about Armijo condition. Armijo condition. Okay, this will not look into detail, but I just want you to have for your knowledge. Okay. Yeah, what we can do is we can try one small example. Okay, so through that maybe you can get an idea what we are discussing about here. Okay, let us take one example so that you can appreciate it better. Shall we take an example? So I will remind you that for optimization, for minimization, we need delta f to be less than 0. That implies dk transpose dot gradient of f at xk is less than 0. Do you agree with me? We have already seen this condition, isn't it? We have already seen this condition, right? Yes. So we will do a problem to illustrate the importance of gradient here. Okay. I mean, I told you we need to go in a certain direction. Now I want to give you an example and show that not all direction help you to reach to the minimum. Okay, we will see an example. We will take the same example. Consider same example. Consider f of xy is equal to x square plus 2y square minus 2xy minus 2x, and take x bar is x comma y. Okay, now what is the gradient here? You have computed it so many times. Dou f by dou x, dou f by dou y. So you will get 2x minus 2y minus 2 and 4y minus 2x. You have computed it so many times. You are getting that, right? Okay. And we computed from the previous step. We computed at x equal to at minus 1 comma 1. At minus 1 comma 1, what is the gradient value we computed? Minus 6 comma 6. Right, minus 6 comma 6. Go back to that, we found it is normal to the tangent, right? Minus 6 comma 6. Fine. And what value of f at minus 1 comma 1? 7. Check it. F minus 1 comma 1, if you put x equal to minus 1 and y equal to 1, you will get it 7. Okay, fine, agree. Now I am asking, which direction shall we go? Which direction to go? I mean, I am finding dk. What is dk here? Okay, so but we have, so as you know, we have to go in a direction dk where it satisfies this condition, that is dk transpose grad f at xk vector less than 0. Okay. So can we take, suppose assume that we don't know the direction. We know, but suppose assume that we don't. Okay. So say let us take dk vector is equal to d1 d2. It's a direction vector. I can take d1 d2 components, right? Now can you tell me what is dk transpose dot grad f xk? What is this value? It's just a dot product, right? So the dot product will be 6d2 minus 6d1. Okay, 6d2 minus 6d1. Do you how many of you understood this? Just a dot product. dk is this vector, grad f is this vector. So just take a dot product of these two. 6d2 minus 6d1. After this, what should I do? Yes, it should be less than 0. It should be less than 0. dk transpose dot grad f should be less than 0. This is what we have been discussing so far, highlighted ones. So what does it mean? It means that we need d2 less than d1. We need d2 less than d1 if you want to achieve minimization. You cannot go any other direction. You cannot go in any other direction you want. You have to go in a direction in such a way that the second component of the direction vector is smaller than the first component of the direction vector. d2 less than d1. Okay. Because we need d2 less than d1, because then that implies that dk transpose dot grad f at xk is less than 0. Okay. So therefore, this is the one of the very most important thing in this whole module. Okay, what I am about to write. Therefore, all dk that is equal to d1 d2 transpose with d2 less than d1 are all valid descent directions. You can reach to the optimum of the function through any of these directions where d2 is less than d1. Okay, so this is one of the most important concepts around here. So we need d2 less than d1, which implies this condition, and you will get this. Okay, so if you want to minimize so let us replay whatever we have learned. If you want to minimize the function f of xy, okay, then you have to go in a descent direction where d2 is less than d1. Okay, then when d2 is less than d1 and you create a vector like this, such directions are valid descent directions. Okay, I mean you can take you cannot take this one. Can you take this one? Yes, you can take. d2 is less than d1. Yeah. Okay, so you can take this. Okay, but can you take this one? You cannot take this because d2 is not less than d1. Okay, so this is a valid descent direction. A valid descent direction. However, this one is not a valid descent direction. Okay, I hope this example gives you an intuition how descent direction works. Okay, this is a very basic and highly conceptual thing. Okay, this way you will only understand. So if anyone asks you later that will any direction in gradient descent works if I go in the negative direction of the gradient also? No, you have to have this condition. So for any other function you can apply this concept. For any other function you will have a different kind of condition. So then you will know which direction to choose with this condition. That is only a valid descent direction. Okay. Good. Good. Okay. So now let us take again the same example, but work for the step size. Now you understood the direction, but as I told you, we need to give importance to the step size. Okay. Let us give importance to the step size in this example. Okay. So consider the same example, that is minimize f of x comma y is equal to x square plus 2y square minus 2xy minus 2x, where you have the initial guess, that is x0 is minus 1 comma 1 transpose. Okay, this is the initial condition I have already given to you. Okay, and we have already found out the minimization point and the value of the function to be minimized, and minimized f value also through Sylvester criteria. But why we are taking this example? To show you different methods we are reaching the same kind of results. Okay, so what you know understood from that, if you take initial point as minus 1 comma 1, okay, what should be the descent direction? Steepest. So d naught we are considering as a steepest descent. Steepest descent. If you consider steepest descent, that means d naught should be minus of grad f. Minus of grad f. Evaluated at x naught. Can you tell me what is it? Can you tell me? Already you have minus 6 comma 6. Minus 6 comma 6. You already did this. No? Correct. Correct. So I was wrong. So what we will do? So minus of minus 1 1. That is 6 minus 6. Is it correct? 6 minus 6. Okay, good, good. That's what I want in the class. Okay. So what we have now, how we will go to the next step, xk plus 1 is nothing but xk plus again hk dk, isn't it? So that is nothing but, in this case, what you will have? So x1 will be nothing but x naught plus h naught d naught. Okay, what is x naught? Minus 1 comma 1. H naught we don't know. D naught is 6 comma minus 6. So this is equal to nothing but 1 minus 6h minus 1 comma 1. Is it correct? I think so. Correct. And I told you that, now observe that thing that I told you before, that this is nothing but a function phi of h. This is nothing but the function phi of h. Do you remember? Do you remember? Shall we go back? Where it is? Here. Yes. Do you remember now? I told you that it will be only a function of phi of h. So it will be a optimization problem only with one variable. Okay. So phi of h. So see, it is minus 1 minus 6h minus 1 comma 1. So it depends only on h. So it's, you have to just minimize phi of h. How will you minimize phi of h? So phi of h, what is phi of h? But I don't think that is phi of h. Is that phi of h? This is, I think I made mistake. This is not phi of h, right? Phi of h is f of x1, no? F, the function value, not x1. Yes, it is f of x1 is phi of h, not x, not x. Here it is x. Agree. So sorry that we made a mistake. So phi of h is nothing but f of x1. That is nothing but f of this one. 1 minus 6h minus 1, 1. Can you tell me what is the value of this? What is the value of this? So that is nothing but f of x is minus of 1 minus 6h and 1 minus 6h, x comma y. So you have to just put this x comma y in this template here and tell me the value. Can we do a quick calculation? So what you will get, you will do minus of 1 minus 6h squared plus 2 times 1 minus 6h squared minus 2 into, this will be plus 2, 1 minus 6h, 1 minus 6h minus 2 times, so it will be plus 1 minus 6h. Isn't it? So what will be this value? It is very interesting. Sometimes see, you don't have to compute everything. It is just a 1 second job. This is nothing but 1 minus 6h squared. This is 2 times of that. This is again 2 times of that. So 2, 2, 4, this is 5. 5 times 1 minus 6h squared. And this is plus 2, 1 minus 6h. Finish. Sometimes you don't have to do extra calculations. Okay. Fine. So, okay. Good. Now you observed, now you are convinced that phi of h is given by 5 into 1 minus 6h squared plus 2 times 1 minus 6h. Do you agree? Okay. Now we have to minimize phi of h. So what we should do? Take the derivative of phi of h and set to 0 to get optimum h. To get optimum h, set the derivative to be 0. If you set derivative to 0, can you tell me what value you are getting? If you take the derivative, what you are getting? So phi prime of h is nothing but, take the derivative of this. Is 0, that implies some h naught is equal to what? Compute. You will set the derivative to be 0. From that you will get the minimum h. You will get a value of h. If you take that value of h, it will make your phi of h minimum. We don't want to minimize the step size. We want to minimize phi of h. No, that is a mistake. Mistake. Apologies. So we have to find a step size h for which phi of h minimizes. And why we want phi of h to be minimized? Because phi of h is nothing but f at the next value. Yes, we want to minimize the future value. We want f of x1 to be less than f of x0. It cannot be greater than x0. Yes, so it has to be less than that. We want f of x2 less than f of x1 also. In that way. So therefore phi of h is a function of h now. Now which value of h you will take so that phi of h is minimum or f of x1 is minimum? So can you set the derivative to be 0 and tell me the value of h? So someone joined the Google Meet also. Is anyone asking questions? No one will ask. Someone joined. How many are playing? Who is not playing? Cannot, what? Okay. Do we get a value? Yes. Any value? H naught should be? Hmm? What you are getting H naught? Hmm. I think you will be getting around 0.2. You are getting. So she got 0.2. Okay. So you will get 0.2. So if you solve this equation, you will get the H naught is 0.2. So what you understood? At 0.2, H naught had a step size 0.2, the function is minimized. Now if it is so, don't believe my words, can we compute the function value? It should be less, right? So f of x naught, you only told me what is f of x naught? F of x naught, I think you computed, no? No, f of x. F of minus 1 comma 1, what is it? 7. Okay. Then can we compute x1 now? Can we compute x1 now? X1 is nothing but x naught plus h naught d naught. Okay. So that is equal to x naught is nothing but minus 1 1, right? H naught is 0.2. D naught is minus 1 1, right? No. 1 minus 1. Is it so? Correct, no? 6 minus 6. Okay. So what is this? Minus 1 1 plus this is 1.2 minus 1.2. So you got 0.2 and minus 0.2. Okay. X1. Fine. Now what is f of x1? That means f at x 0.2 and minus 0.2. That means our next step. So this is f of x naught. I want to compute f of x1. Can you tell me this value? F of x1, that is my 0.2 minus 0.2 from this step. But what we did here? No, our question was, see, we set phi of h naught equal to 0. Why we set phi of h naught equal to 0? To get the step size at which phi of h is minimum. So we found from this equation, after solving that, h naught equal to 0.2 is such value. Where h, if you take h naught is 0.2 step size, then phi of h is minimum. No, I did not say step size minimum. I said find a step size h naught for which the function phi of h is minimum. Why I am telling that phi is a function of step size h. Actually, you want to maximize the step size. We don't want to. we are not maximizing or minimizing the step size. We are finding a value of a step size for which phi of h, that function, is minimum. Our idea is to make phi of h maximum or minimum. We are not bothered about h minimum or maximum. We want to find a value of x for which f of x is minimum or maximum. We don't want to, never I told x should be minimum or minimum. I always concentrated on f of x should be maximum or minimum. The output should be maximum or minimum. The f of x is the input. Input we cannot say it is minimum or maximum. Output we can say, output is loss function, right? That loss function we have to say whether loss function is maximum or loss function is minimum. H we cannot say, H is input. H is the input to phi. But you have to know, but you are telling that here is the optimum. But in real situation, will you know that where is the optimum? So how will you tell how much to go where? That I understand. If you know here is the final optimum value, okay, then you know that yeah, I can jump directly with one step there. But if you don't know where is the optimum, I will give you an example. Just save this question. Another graph approach is come. Okay, there you will see, there you will confuse how to reach there. Okay, I'll tell. So yeah, you are thinking correctly. I understand the confusion where you are. But the idea is a priori. A priori means from the previous ideas, we will not know where the optimum value is. This step we are doing. Tell properly.
Like, suppose we didn't take the step size and we got f of x a plus 1. And we have to just take if it's less than or greater than the base f of x a.
That also you can. That also, but that those condition you have to check again and again multiple times. That will be computationally expensive. These methods prove to be computationally expensive. That is what I am trying to show you. I will show the Python also. At the end of the class, all your question will be answered. Just hang on. Okay. So you understood. So what value? Tell me. What value you got till now? F of x1 is minus 0.36, right? Minus 0.2. F of x1. This one is minus 0.2. You are telling? Why? Compute correctly. Compute correctly. So what you are doing? I hope you are doing like this. That is 0.2 squared plus 2 times minus 0.2 squared minus 2 into 0.2 minus 0.2 minus 2 times 0.2. So this is 3 times 0.2 squared minus 2 times plus 2 times 0.2 squared minus 2 times 0.2. This is 5 times 0.2 squared. 2 times 0.2, 0.252, 5 into 0.2, 1 minus 2. Okay, minus 0.2. Good. Okay. But can you see that? Can you see? Can you see that f of x1 is less than f of x0? Minus 0.2 is less than 7. So how drastically the function reduced if you went through that optimum step value h. Okay, got the idea? And if you told that next is go do that and check if f of x1 less than f of x0. Suppose it happened, you are lucky. Suppose it did not happen, what to do? Come back and again repeat for another value of h. Suppose there also did not happen, then again come back and do. Okay, how much will do like that? Is for one iteration, right? Now you have to do some 10-20 iteration like that. So 10-20 iteration and maybe 5-7 times. So easily 300-400 iterations. If it fails, if it fails, it's easy, but you have to be extremely lucky to find that direction. Okay. So the idea is like that you go to the second round, compute x2, that is equal to x1 plus h1 d1. Okay. Again, find what is f of x2, take it as a phi of h1, okay, some function, then again minimize phi of h1, that means find value of step size h1 such that phi of h1 is minimized, right? Same thing, continue, keep on doing it. The more and more steps you do, how will you reach convergence? So the criteria for convergence, that means the criteria to stop it or reach the optimum is that the modulus, that the norm of the direction dk will be less than some tolerance value. It will become, every time it reaches to the optimum, the direction will be getting smaller and smaller, isn't it? You approach more and more and more, it will get smaller and smaller. Okay, so then this is the stopping criteria to check. This I will show you in Python also. Okay, so this is what we are doing here. Okay, you understood this method. So what are we doing in this method? In this method, at every step, we are updating the step size. We are finding the step size for which the function phi h attains the minimum. At every iteration in this method, at every iteration, we are updating the step size. We are updating the step size hk at every iteration to reach minimum of phi of hk at every iteration. Is everyone understanding this? Everyone understanding this? So this is the main catch here. At every iteration, you are finding the optimum step size for which phi of h is minimum. And therefore, this method is computationally very expensive because at every iteration, you are minimizing phi of h. At every iteration, you are minimizing it. Therefore, it is computationally expensive method. Okay. Fine. So if it is computationally expensive, what can we do? Can you let me know? You understood now? This is computationally expensive, right?
So we are only updating the steps as well. The directions.
The direction will not be constant because direction is grad of fxk and xk is updated at every step. So gradient will automatically be updated and dk will automatically get updated. Changing. So that you will see in Python. When I show you the graph, you will see in this direction, you will see. That's what I am doing. Hang on. I will show you. Just one small method is there. After that, we will go to Python and show you. Okay. So now do you agree that this method can be computationally expensive? This method can be computationally expensive, right? Like so. So this method is computationally expensive. So what can we do here? What else can we do? Why it is computationally expensive? I just want to know whether you have understood all the things or not. Can anyone tell? Hmm? Why it is computationally expensive? No, it is computationally expensive because you are operating the step size at every iteration. You are finding hk such that phi of xk is optimum. Okay, fine. Do you agree? Okay, fine. So we'll see this. So therefore, it's a computationally expensive problem. Okay, it's computationally expensive. So therefore, what other authors thought, other scientists thought, how can we reduce the computational complexity of this algorithm? Therefore, people went like, why are we so fixed to optimize at every step? Why don't we partially optimize it? Therefore, this idea led to partial optimization. Partial optimization concept. Okay. This led to partial optimization concept. Now, what is partial optimization? We'll tell you here. So this is where we are telling it as a backtracking. Okay, backtracking line search criteria. Line search means along a particular direction we are searching where is the optimum. We are searching where is the optimum. That means search. That means we don't know a priori where is the optimum. Therefore, the motivated to use the word search. Okay, backtracking line search. Okay, and this is known as the Armijo condition. So I hope that whenever you are trying to learn any conceptual machine learning textbooks, okay, so in conceptual machine learning textbooks where they don't just use the black box models, I mean not just CNN or anything, just apply and it will classify your images, where people actually built the CNN models. Okay, how they built it from the scratch, the algorithms. There you will see these minimizing loss functions, and they have used. There you will see the word Armijo conditions. Okay, so in the evolution of the machine learning algorithms, these are very useful. Now that you are using just the black box models, you don't see it, but inside them, in the building process, it is highly used. Armijo condition. Okay, so it is not a method; it is a condition which we use with the gradient descent method and make it more computationally efficient. You got that idea? Armijo condition is a condition which we pair with the gradient descent method. Okay, which we pair with the gradient descent method to make it computationally efficient. So this is the whole gist of the work which we are going to discuss. However, we will not spend lot of time or any problem to do, because these things are we cannot do by hand, because these things can only be done using Python code in a for loop until a condition is met. So we can only appreciate this method through the Python codes, like through computational code. Okay. Fine. So how this works, I will just give you an idea, and then we will directly go to the Python implementation. Okay. So just hang on for this one. Soon we will, reach. Okay. So here, what is the catch in this method is in this criteria. Okay, in this criteria, we do not look. We don't. Okay, look for the minimization condition at every iteration. We don't look for the minimization condition at every iteration like you did previously, that minimize phi of h, okay, and compute h at every step. That we are not doing here. So what are we doing here? So rather we are implementing, we are implementing partial optimization. Now what is this? The term partial optimization means. Okay, what do you mean by this partial optimization? Here, okay, we'll see this. Okay, so we enforce this condition, as you know, like where it is. We in this condition also we will enforce that f of xk plus hk dk is a vector is less than f of xk vector, as you pointed. Okay, but we do not minimize f of xk plus hk dk. But we do not minimize f of xk plus hk dk. Like this was phi of h, right? This was phi of h. We will not do that. At every step, we will not minimize phi of h in these steps. Okay. So what we will do? So fourth condition is, this is a non-trivial condition. We will not, I mean, a heavy mathematical argument is there, which we are not discussing at this step right now. And it is a high non-trivial condition, okay, of armature. So here I will just write it, I mean, just to show you. Okay, we will just write the condition just to show you, but we will not go into the details how we got this condition. Okay. So fourth is, rather than that, Armijo condition suggests, okay, Armijo condition suggests, okay, what? That f of xk vector plus hk dk, okay, is less than or equal to f of xk plus, there is some additional terms here, which is highly non-intuitive, but I will write for you. But you have seen that kind of things before. Okay, that is some beta term. Okay, and then h, then dk transpose and gradient of xk. So you know this is the directional derivative already. Okay, and then h also you have seen it, but we are adding a beta times that term. Okay, I mean we don't know that. This is the Armijo condition. I mean, why? Then we have to do the whole proof and see why it is. So this is the efficient condition to check. If you use this condition, then you will prevent updating the h at every step. Okay, therefore we use this condition. But we are not going into detail how to derive this condition and why we will believe this condition. It is derived by Armijo, we are just knowing it. Okay, I mean, we'll not go through detail. If you're interested, we can do it, but maybe towards the end. Okay, but just for now, you can appreciate that previously we needed up to here, right? Previously we needed up to here only, yellow shaded region, but now we are telling that we are adding something more here. We are adding something more. Okay, now, no, it is a plus, no? There is a plus. That is the extra term. I mean, yeah, you are correct. But this is our condition. This is our condition. Yeah, that condition is the sufficient one. We will check that one. I told the second one just to mention that we do not minimize at every step f of xk plus hk dk, but instead of the second step, we will ensure this one. We will not check that. We will check this. We will not check both. We will check only the Armijo condition. Okay, we will only implement step 4. We will implement that in Python also, and you will see how drastically the number of steps reduced computationally. I will show you that. Okay, so you can see that Armijo condition with gradient descent is much more efficient than gradient descent itself. You are appreciating that, no? Armijo condition when applied to gradient descent is much efficient than gradient descent itself. That we will see. You will see that gradient descent might take 70 steps to reach optimization, whereas if you use Armijo condition with gradient descent, it will take some 40 steps. That we will show in Python. Same example, f of x1. Same, that ellipse example. So what is this beta? This beta is nothing but an additional parameter. Okay, this is an additional parameter, and the Armijo said that this beta should lie in between 0 and 1 only. You cannot take any other value. I mean, just with a pinch of salt, you can take it that this is true. Okay, I mean, we are not going into the detail of the proof why. Okay. So how the algorithm goes. So this is the how the algorithm goes, the steps. Okay, how the algorithm goes. So this is the algorithm, new algorithm, up to date algorithm we will check. Okay, first is check whether the Armijo condition is satisfied or not. That means check equation 1. What is equation 1? This is equation 1. Is it good? So check whether the Armijo condition is satisfied or not. That means check if first equation is satisfied or not. Okay. Suppose it is not satisfied. Suppose it is not satisfied. If it is not satisfied, then only you change the step size. You saw the intelligent criteria here. Don't change the step size at every iteration. Rather than what we can do, partially change it. When you can partially change it, check when Armijo condition is satisfied. If Armijo condition is satisfied, well and good. You don't need to change the step size. If Armijo condition is not satisfied, then only change the step size. So how will we change the step size? So scale it. Okay. Then use the step size. Then h step size, change it to some tau h. Scale it. How will you scale it? Tau is some value in between 0 to 1. That means reducing it. That means we are actually reducing step size, reducing h. To be honest, in numerical methods, always step size has to be reduced, never increased. Okay. I mean, if there is a bound in step size. If you keep on increasing step size, I hope you have seen in your previous semester also. Okay. Step sizes are never taken as 1.5, 2, 3, 4 like that. It is always taken in the order of 0.1, 0.01, 0.001, 10 to a minus 4, 10 to a minus 4. Always reduction in step size. Because these are numerical schemes and highly nonlinear schemes, so you don't know that it will work linearly nicely. Okay, it may be that if you decrease it so much, it will not converge. If you increase also, it won't converge. There has to be a balance where you have to find. So till now, only optimization method can help you in that, finding the appropriate steps. Otherwise, in first semester numeric methods, you have taken step size like given you, no? Take h 0.01. How? Why? Because you know that the method will work if you take 0.01. But you can take 0.00001 also, right? But in that case, you will need 20-30 steps. By that time, exam will go. So you have to think about that. Okay. So third step is, okay, you made this h to tau h, reduce the scale, the step size. Then what you do again? Check the Armijo condition again. Okay. Continue this first and two steps. Continue till Armijo condition is satisfied. Till Armijo condition is satisfied. Okay. Actually, I can give you an idea. I can give you an idea about the Armijo condition, why it looks like equation 1. Okay. So what we are trying to do here is we are trying to make the difference of this and this. Okay. We are trying to make the difference. Okay. So that means I will write here so that you can see what I am trying to do. I am trying to make the difference, trying to make the difference of f of xk plus 1 and f of xk, okay, less. Isn't that what we want? Isn't that what we want? Then if that happens, if the difference gets less and less, that means you are reaching a convergence. If the difference between xk plus 1 and f of xk is less, getting less and less, that means you are ensuring convergence. That means every step you are reaching near. Okay. To do that, they introduced. Okay. They did that by multiplying h artificially. This is said by Armijo. Okay. So trying to make the difference of f of xk plus 1 and f of xk less by multiplying h artificial. So can you write equation 1? Like, can we write like this? Like f of x k plus 1 minus f of xk, okay, is less than equal to beta times h, what? That whole term, whatever term is there. Okay. So if we are multiplying h, we know h will be very small quantity. Okay. If you have that h term, then you are forcing the difference to get smaller and smaller and smaller. That's a very nice technique he adopted. Okay. He thought that I want to make the difference between the two functions very small. To do that, why not I use the step size also? Because I know step size is also small. If I multiply whatever with the step size, that will also get small. So why not I introduce that with the difference of the functions? That's a very intelligent guess. I mean, through a lot of years of experience, every day working on this and this, they get this. Okay. Not that intuitive for us to think how they got. Okay. Anyway, so what we will do now is we will go to Python. Okay. To understand this. Let me get to the point where we have the optimization. Yes. So let us start with this. Let us start with this one. So let me zoom for you. I hope you can see. Is it clear? Is it visible? So what we are doing here, we are treating gradient descent with a constant step size. Okay, remember the constant step size, like you told. Okay, like why we are changing? Why we need to change anything? Just to go with normal things. Okay. So what we did is we went like that. Okay. So what we do, maximum iteration, we are taking 10,000 steps. Epsilon, that means the convergence criteria 10 to the power minus 6. Okay. And step size, we are taking 0.01. Okay. I mean, step size is 0.01 means for any next methods and all, the step size will be 0.01 fixed. At every step, it is 0.01. Okay, fine. So then objective function means the function we want to minimize. Can you compare with your notebook that it is exactly the same function which we did in class? I have taken x0 as x and x1 is nothing but y. Okay. X0 is x and x1 is y. So it's a lambda function in Python. So you can see x0 double star 2 x0 squared x square plus 2y square minus 2xy minus 2x. That's the objective function. And you can compute the gradient also. Gradient is a vector, so you got 2x minus 2y minus 2, comma 4y minus 2x. I am giving the gradient function also. Okay. Now what I do? Okay, I am taking x as an NP array. Okay, and then you see I am using a for loop. Okay, in that for loop I have written in the range of max it, and maximum iterations is around 10,000 steps. I have taken defined on the top. Okay, what I am doing in each step here inside the for loop, I am writing gradient function of x. That means I have computed gradient. Okay, I have computed the gradient here in this step, computed the gradient at x, and then I am computing b. B is nothing but the norm of the gradient. Norm of the gradient. Gradient is a vector, you can compute the length of the vector. That is nothing but the norm. Okay, so if b is less than epsilon, epsilon is 10 to the minus 6. If gradient is getting closer to 0, then break it. If you have reached less than the tolerance, break it, because that's when you have already achieved the optimum. Okay, else if you have not achieved the optimum, gradient is not smaller than the 10 to the minus 6, use numerical method, use gradient descent. Okay, what is gradient descent? Xk plus 1 is equal to xk minus the step size and the gradient. Huh? Huh? Yes, it is. Xk plus 1 is equal to xk plus hk dk. Hk is step size, dk is minus of gradient. So minus of gradient. So already dk is introduced inside. You got it. So like that we do. And what I am printing here? I am printing here the iteration number. Then what is the x value we are getting? And the norm of the gradient, b. B is the norm of the gradient. So, okay. So you can see minimum value, then I am printing objective function of x. Because after coming out of the loop, after it breaks, that will be the optimum value. It came out of the loop after that only, right? Okay. So minimum value this, and what location we got that is x. Okay. And we are printing it. So here you are seeing this is the iteration value, and this is the x value, that is x1, x2, that is xy. Okay, and this is your, what is it? I forgot. B, norm of gradient, third column. Okay, so let us go through the steps. Okay, and I will show you how many steps we needed to optimize this. Okay. Objective function, that's same in the classroom. We take the same example here in classroom. Okay, so let us see 30-40 iteration happened, but the norm of gradient is still around 2.07. Very high, very high. Still let us go. Okay, still let us go. So now it has reduced a bit, right? At 200 steps it got 0.55, right? Then try to go more slowly. So now you are getting a feeling that with increase in number of iteration it is decreasing, right? What you can do is plot the norm of the gradient with the number of iterations. How it is decreasing. We are seeing it is decreasing, but it is uniformly decreasing, or it is decreasing in a zigzag way. Is it smoothly decreasing or non-smoothly decreasing? That question I can ask you. Huh? How? So therefore you will see some jags, right? So it will be interesting to plot. Maybe I can share this code with you. Then I suggest you plot this additional argument after learning this. Okay. So it will take a lot of time. So what I will do is I will show you the end. Yeah. Yes. So can you see now that in 1933 steps, okay, the function value is 2, 1, okay, almost, and the norm of gradient is 1.004 into 10 to the power minus 6, because that's the tolerance we had set. Okay, so can you see that the same function which you can do in your notebook using Sylvester criterion took 2000 steps if you use fixed steps. Okay, so you should not use fixed steps. Okay, so this is the reason why we should not use fixed step size, even though it is convenient for us. Okay, now what I suggest is, let us use Armijo condition with gradient descent. What was Armijo condition? Armijo condition was f of xk plus 1 is less than equal to f of xk plus some beta, that is parameter, okay, h, then dk del f dot at xk, right? This one. And our job is to minimize these differences by peaking this h. Okay, and beta can lie in between 0 and 1. dk already know about it. Okay, fine. Let us use this condition. What we thought of this condition, I will remind you again. Check, first step is check for Armijo condition satisfied or not. First step. If it is satisfied, well and good. If it is not satisfied, what to do? Update the step size. How you will update the step size? H now will go to tau of h, where tau will be in between 0 and 1. Maybe h is 0.1. Then maybe tau, if you select like 0.3 or something, then h becomes 0.3 into 0.1, so 0.03. Right? You decrease the step size, right? By decreasing that, again check the Armijo condition if it is satisfied or not. Do that till you get Armijo condition satisfied or not, then only check the optimization. Now let us look into the code that whether it is done or not. Okay. So you can see here, this is the Armijo condition. Okay. So I am doing line search, gradient descent. So beta I have taken 0.001. Beta I have taken 0.001. Beta can be any value in between 0 and 1. So beta I have taken to be 0.001. Step size I have taken to be 1. Okay, fine. Let us see. Trial 100, tau is 0.5. I mean, every time if did not satisfy, the step size will be reduced by 0.5. H, then 0.5 h means h by 2. Again, if you multiply 0.5, h by 4. Okay. Here I am already defining this objective function. Okay. Don't worry about this. So see this one, f of x1 is objective function at x. F of x2 is objective function at x minus step size into gradient. Okay. Then this additional term is written as c. This additional term is written as c. That is minus beta times step size and np dot gradient and gradient. That is del to f. Because dk is nothing but grad f. So del f times del f. Okay. So then we are checking the difference here. fx2 minus fx1. See the Armijo condition I told you, when I did not tell you that look into the difference, it was looking at something very abstract, right? But now when I told you that Armijo condition, why Armijo thought of it like that? He wanted to make the difference between the two steps or iterates very small. So therefore here we are checking if the value of the function at the previous step minus the value of the function at the next step, is it less than or equal to c? Is it small enough? Because c has the step size in it. So c, step size I have taken to be 1. Okay, but here it is scaled, right? So if this is Armijo condition, if fx2 minus fx1 less than or equal to c, that means here Armijo condition is satisfied. If Armijo condition is satisfied, good, break and continue with the gradient descent. If it is not satisfied, change the step size by multiplying tau. Okay, tau. Okay. Then other things are same as gradient descent as per the above code. All other things are same as gradient descent which you did. See, objective function you already did, lambda function, gradient descent already computed, right? Then what you do? Gradient you are storing, b you are storing the norm of the gradient, and when you will stop, the stopping criteria is norm of the gradient is less than or equal to some epsilon. some 10 to the minus 6, right? So that you are checking here, and you are doing this time. Okay. Now let us check and plot these things. Yes. See. Okay. This is something very interesting. So you can see the minimum value it attained at -2, and location is 2, 1. You can say 2, 1. Okay. And how many iterations it took? Only 44 iterations. Previously you took how much? 1993 again. Okay. So 2000 iteration it took for constant step size, whereas if you use partial optimization with Armijo condition, it took only 44 iterations. 2000 to 40 iterations. How much? 1 by 50? 1 by 50? How much percentage improvement? Okay. So how it did it? Okay, how it did. You started from here. This is your initial condition. You see how quickly Armijo condition led it to. Then you went again. Then you see the next step it took. It is a perpendicular. Then from here, next step it took. It is a perpendicular. Next step it took perpendicular. Perpendicular. But know that the length is decreasing every time. The length is decreasing here, then smaller, then reach optimum. Okay. I hope you appreciate that even though you are starting from here, you are minimizing your optimum value is at here. It could have, but you cannot do it. I mean, it looks, you are only telling because you already know that it is here. But a priori you don't know. A priori it is like your eyes are closed and you told, yeah, you find the door where it is. So how will you, where to go?
You know where the direction of the
But you don't know.
yeah, I don't know the position, but I know the direction.
Huh. So how will you do?
This
Okay.
example you will provide.
So this is the door, okay, and this is a plane actually. Edge of the plane, this thing is 9,000 feet up, okay, 9,000 feet up, and there is a door here. Through this door, if you go, you can safely go to the 0th floor, okay, ground floor. If you fall from this, go, okay. So you are walking from here. Suppose you know the direction of this door, okay, you can jump at least, okay. But that is very lucky. If you are that lucky, then why we are studying all of this? If you are that lucky, then why CNN is 94% accuracy? It can give you 100% accuracy CNN. There would not be any loss. Why there is loss? Isn't it? There is some loophole. Right? If you get full accuracy, then you can achieve it. But that is never achieved. Always there is a loss. Always. Anyway, see how it is performing. You don't need to worry. Here also it is same good things. Yeah. In 44 iteration also it converged. So actually, yeah, this is how it looks like. Actually, you take lot of ellipse. I hope you have drawn this ellipse in your Desmos. Okay, and you can see this is where f of xy equal to 0. This is where it is 6, 8, 10, 12, 14, 16, 18, like that. It is increasing this direction. So the gradient will point in this direction. Gradient will point in this direction. Okay. So therefore, if you have to minimize it, it should be opposite of gradient. So therefore, you know that when you are minimizing the function, it is not anywhere across this space. It is always opposite to it towards you. I mean, through the looking at the graph, you can visualize this. Why it is true? Why not it is wrong? Okay, how can you testify that whatever you are looking at computationally is correct? How can you explain that? So you can see here that you started from here, but suddenly it went to this contour, then perpendicular directions decrease in size and reached this optimum here. It's very interesting. So therefore, optimization uh, is interesting because these are highly nonlinear functions. You don't know where to go, but these functions work so nicely that wherever you start from, if you take the correct direction and proper step size, you can always reach to the optimum. Okay. This is a depiction of visualization why these methods actually work. Okay, and why not? It is just some mathematical statements. You just do some proof and computations. Why it actually work when you put that visualization? It is interesting. Okay. Huh? This is 2D. F of x comma y, no?
Direction of the optimum.
No. Gradient. Steepest direction.
If you ask me that we are starting from here and our opinion is there, then why the direction was shown this way and not this way?
I mean, see, that is, how can I say? No, that is what we looked at. That is what exactly we looked at in the start of the class. Yes. So see, here is your optimum somewhere. Okay. But here we took the tangent. Okay, here we took the tangent. Then we showed that gradient is perpendicular to the tangent. So opposite of that is the gradient direction. Okay, steepest direction. But here what you are asking is also correct. That why we have to go in this direction. Okay, maybe if you compute, maybe I'll think about it. I don't have an answer now. Maybe I'll think about it in tune. Okay, you are asking that why not the direction is like this? Why the direction is not like this? Okay, that I will think. Okay. Anything else? Now this is also good. just reach, yeah, finish. Eh? So yeah. So what is this? Maybe I have to check. So no, it depends on the starting point also. Yeah. It depends on the starting point also. Yes. It depends on the starting point also. See, the starting point is different here. You cannot predict where you start, you will reach because it is highly non-linear problem. It has square terms, xy terms. You cannot say. If it is ax, it is linear. Okay, perceptron. This will be next soon. Okay. Okay, I will share you this. I will share you this code. Next class, okay. Next class, we will learn about n-dimensional Newton's method and why n-dimensional Newton method can be sometimes better than gradient descent method. We'll learn about it. So we can stop here. No? Okay. We can stop here.